The reason why I chose this topic is because there is in the market there's many the misconception about the ratings definition, and people are confused. So hopefully today we'll have a better understanding and discuss in details about the different parameters that has to be considered. Firstly, let's look at the different factors that has to be considered for a genset selection. These are genset parameters, genset application and ratings, ambient conditions, alternator installation class and temperature rise class, types of starting methods used for motor loads. What are the parameters that has to be considered, or what you should check first before selecting a genset rating? Specify the required number of phases if it is a three-phase or a single-phase genset. Specify the required voltage, 400 volt, 415 volt, 480 volt, 380 volt. This may vary depending on the region and country. Specify the required frequency if it should be 50 Hz or 60 Hz. This also differs depending on the region. Specify the genset capacity. Let's have a look at the different ratings definition as per ISO 85281. There are mainly 4 ratings which is defined by ISO. The first one is prime power rating. What is prime power? Prime power is the power available for unlimited hours usage with an average load factor of 70% of the published prime power over each 24-hour period, and also a 10% overload is permitted for 1 hour in every 12 hours of operation. The loads are variable. The typical peak demand is 100% of the prime power rating. The typical applications are in industrial, pumping, construction, rental. As you can see in the graph here, A is the maximum power available, B is the permissible average power, C is the actual average power. What is emergency standby power? Emergency standby power is the power available and is limited to 500 hours annual usage with an average load factor of 7. I still can get a message that we can't hear you. Am I audible enough? You can't hear me? Okay, perfect. So yeah, as I said, it is the standby power is limited to 500 hours annual usage with an average load factor of 70% published standby power, 70% of the published standby power rating over each 24-hour period. It is up to 300 hours of annual usage. The load used in this is variable. The average load factor over 24 hours is 70% of the published standby rating. The maximum expected usage is 500 hours per year. And it is used, the typical applications are in buildings, schools, banks, etc. Continuous power. Continuous power is the power available for continuous full load operation. It is applicable for unlimited number of hours. The average power output is 100% of the base load power rating. The load is constant and is used in applications like data center, irrigation, etc. Okay, what are the different other factors which have to be considered for a genset selection? The different factors are altitude, humidity, salt, dust, and heat. Going into detail into each of them, as you can see, all generators operating in altitudes above sea level will be derated with a deration factor. Each machine has a different derating factor as per manufacturer recommendation. As I already mentioned, these factors, The duration factor vary from one manufacturer to other. In case if you want to know the duration for each particular engine or alternator, you have to contact with the manufacturer so that they will provide you the data, the duration curves, and from there you can actually know what is your duration at the required site conditions. Humidity. Condensation resulting from humidity can present a problem for standby units or units that do not run frequently. Space heaters should be used to raise the temperature to 5 degrees Celsius above the ambient temperature. Salt. Special alternator installation treatment may be required. Dust. Dust like, for example, cast iron dust, carbon dust, powdered graphite, coke dust, lime dust, or wood fiber or quarry dust. Use heavy duty air intake filters, and this is like standard in most of the manufacturers. They use heavy duty air intake filters. So heat, when the temperature of the ventilating air exceeds 40 degrees Celsius. Derating of the generator may be necessary. Among all these factors, the most important one is the, while selecting a genset, is the altitude and heat. These are the two factors which you have to really take into consideration while you select a genset. You have to go back to the manufacturer, get the derating factors. I can see a question why there is no temperature mentioned on the duration graph if it only denotes alternator duration percentage. Sorry, this graph is from the engine manufacturer, Perkins engine manufacturer. Here, it's not a complete, it's just a small snippet. Moving forward, I'll show you in detail how to do a duration calculation. You can do it by yourself. You don't have to go back to the manufacturer or to the your supplier or technical support each time. So we'll go through an example how to do the duration calculation. Yeah, as you can see here, this is the engine duration chart, and this gives the duration at altitudes from 0 to 4,500 meters above sea level at different ambient temperatures. These are the different ambient temperatures. The starting first one is 25 at 25 degrees Celsius ambient temperature, 30 degrees Celsius ambient temperature, 37 degrees Celsius ambient temperature, 43 degrees Celsius ambient temperature, and finally 50 degrees Celsius ambient temperature. The most common ambient temperature in Dubai is the 50 degrees Celsius, as you all know. In Kenya, it's mostly 43 degrees Celsius. This is the alternator duration table. In this, you can see the alternator duration applicable at different altitudes, ranging from 1,000 to 4,000. Why is it starting from 1,000? Is that Larisime alternators are designed in such a way that they have no duration up to 1,000 meters above sea level. Only after 1,000, there will be a duration or a derating factor which is applicable. These are the durations applicable for different ambient temperatures: 25, 40, 45, 50, 55, and 60. Okay, let's do a calculation. Like, how can we calculate the net output of a genset at different at the required site conditions? In this example, I have taken the requirements at 1,000 meters above sea level and 50 degrees Celsius ambient temperature. This could vary from site to site or from region to region. It depends. This is a general way how to do a duration calculation. The first step being you have to check the standard genset ratings available at STC. It depends on the from supplier to supplier. You have to check the genset ratings at STC. This is Jubilee Pro standard genset ratings available. As the requirement is battery charging alternator power typical, the net engine power, the compression, flow, exhaust. All these are not the main ratings which is required while doing the duration is the typical genset output at STC, which is 25 degrees Celsius. So as you can see here, this genset gives an output of this engine gives an output of 1010 kVA prime and 1125 kVA standby. Next, we'll have to look at the engine duration curve for this particular engine, which is 400830 tag 2. Here, as you can see, there is no duration at the specified ambient temperature and altitude. Am I audible enough now? Okay. Okay, yeah. So there is no duration applicable at the specified ambient temperatures in this example. Say, take 1,000 meters above sea level and considering 50-degree ambient temperature, as you can see, the duration percentage is 0, or the derating factor is 0%. Thus, the engine net output after duration at 50-degree ambient temperature and 1,000 meters above sea level is 1010 kVA prime and 1125 kVA standby. Now, in the next step, we'll have to check the alternator rating table from the alternator manufacturer. Here we have the 𝐂𝐬𝐧𝐭𝐚, which gives an prime output of 1000 and standby 1100 kVA. The main factors determining the alternator selection is the insulation class and the temperature rise class, which I'll be going into the detail later in the coming slides. Let's have a look at the derating factors applicable for the alternator. As I said earlier, there is no duration up to 1,000 meters for Larry Summer alternators. The duration is applicable after 1,000 meters above sea level, say for 1,500, 2,000. Say you have your site is at a is considering in Africa, say the altitude is 2,500 meters above sea level. In that case, you will have to consider this 0.922 as your derating factor. And for ambient temperature, for there is no duration up to 40 degrees Celsius ambient temperature. That is the reason why you can see 1 as the derating factor. Above 40 degrees Celsius, there is a percentage applicable. In this example, as we need 50-degree ambient temperature, we'll consider 0.946, which is the derating factor. Thus, the net output, alternator output at these conditions, which is 1,000 meters above sea level and 50 degrees Celsius ambient temperature, will be 946 kVA prime and 1040 kVA standby. The net output of the genset will be the lower of the net output of the engine and the net output of the alternator. As you can see here, net output of the alternator is 946 kVA prime, whereas the net output of the engine is 1010 kVA prime and 1125 kVA standby. You have to choose the lower of these two. Thus, the net output will be now 946 kVA prime and 1040 kVA standby. Okay, now let's have a look at the NEMA MG1 installation classification. NEMA, National Electrical Manufacturers Association, recognizes 4 classes of electrical installation of the alternator, which is Class A, Class B, Class F, and Class H. Each of these classes have different characteristics, but the accepted common feature is an anticipated minimum life expectancy of 30,000 hours. Letter signifies the maximum allowable winding temperature while the alternator is operating. If exceeded, the insulation will break down, resulting in winding burnout. In the next slide, we'll have the look at the temperature rise, the different temperature rise that is classified based on the insulation class. Here, as you can see, there are two classifications for both. There are actually both for continuous rated and standby rated. For class A, B, F, and H. For, if the genset is continuous rated, the maximum allowable temperature rise for class A is 60 degrees Celsius, for class B is 80 degrees Celsius, for class F is 105 degrees Celsius, for class H is 125 degrees Celsius for a continuous rated generator. Whereas for the standby ratings, as standby duty results in fewer hours of operation, NEMA MG1 allows alternator windings to operate at 25 degrees Celsius higher than for continuous duty applications. If used for continuous duty or prime power, the standby alternator's useful working life will be considerably shortened and reliability may well become an issue. Most manufacturers of alternators supply the market with Class H insulation, which meets most of the normal applications and duties that are encountered. So, as you can see here, for the standby ratings, there is the as per NEMA classification, a 25 degrees Celsius addition is allowable on the continuous rating, which is 60 plus 25, 85. For class B, 105, for class F, 130, for class H, 150. This is another classification definition for the insulation class and temperature rise class as per IEC standards. It's very similar to NEMA. And as per IEC, also there are different classes, which is class Y, A, E, B, F, H, which is similar to NEMA, but just there are some more additions. And the insulation class is defined with specific temperature for a thermal endurance of 20,000 hours. Insulation qualification is based on the design and manufacturing process. Insulation gives the maximum acceptable temperature regarding the windings insulation system. For class Y, the maximum temperature that is allowable for class Y insulation class is 90 degrees Celsius. For class A insulation class, it's 105 degrees Celsius. For class E insulation class, it's 120 degrees Celsius. For class B, 130 degrees Celsius. For class F, 155 degrees Celsius. And finally, for class H, 180 degrees Celsius, which is the most common one and is used by most of the manufacturers. Here we can see in this graph the allowable temperature rise as per IEC standards. It's similar to NEMA, but to have a quick look, for class H insulation class, as already said, the maximum temperature it can withstand is 180 degrees Celsius. And considering class H temperature rise, it can give up to 125 degrees Celsius. For class F, the maximum it can withstand is 155 degrees Celsius and a temperature rise up to 105 degrees Celsius on the continuous rating. For class B, the maximum temperature is 130 degrees Celsius and a temperature rise of 80 degrees Celsius on the 40 degrees Celsius ambient temperature. So the last topic of today's webinar is the different types of starting methods that can be used for the motor loads. First, let's have a look at the basic characteristics of motor loads. Motor loads cause difficulty because a motor draws high current when started at full voltage. Starting current is typically 6 times a motor's rated full load current, and this inrush current stays high until the motor reaches about 75% of the rated speed. When a motor is started on normal utility power, the high inrush current will cause only a small voltage dip because the utility is a more of an infinite energy source. However, when a motor is started on genset power, the high inrush currents can result in large voltage dip that can inhibit the motor from reaching its operating speed and might cause the genset to shut down if it's not properly sized. So, in order to overcome these, we can what are the different methods of starting which can be used for motor loads? We'll be having a look on those in the next slides. The different starting methods are direct online, star delta, soft starters, VFD, which is variable frequency drives. Okay, what is direct online starting? Direct online starting is starting method where this genset is where the motor load is connected directly to the genset. There is no there's no other method there's no other connection. It's just connected directly to the supply. As you can see in this graph, when using DOL starting, the starting current is 6 times the nominal current value. So this is if a dual starter is if it's connected directly, the current is very high. But if a soft starter, if a star delta starter is used, it can reduce the starting current to 1/3 of this value. As you can see here, in star delta starting, the method used is it is connected to the genset. The motor load is connected to the genset in a star configuration at this time of starting. That is, you're reducing the voltage, and once it reaches its rated speed, once the motor reaches the rated speed, it is switched to the delta configuration. There are the different advantages and disadvantages of both are in dual starting method, the design is simple, it is less expensive, whereas the design is complex. Since it's not complex, it's a little more components are used for delta starting, and it's expensive compared to DOL. In DOL, the starting current will be the full load current. Oh no, actually 6 times the full load current, and the in star delta it will be 1/3 of the current, and the start in DOL the starting torque will be full load torque, and the in star delta it will be 1/3 of the torque. Whereas in DOL you only require one contactor. It's simple, the circuit is simple. Whereas in star delta you will require a minimum of 2 contactors. It's a little complex and it's expensive as compared to DOL. The next starting method is soft starters. This type of starter is most popular and provides exceptional operating flexibility. It is a form of reduced voltage starter that utilizes silicon control rectifiers to increase the voltage at a predetermined rate. Limits on the starting current can also be adjusted to increase the system performance. In this graph, as you can see, this is when the motor is connected directly to the genset, and when it is connected through a soft starter, the current is reduced at the time of starting. Variable frequency drives. Variable frequency drive is the most efficient starting method. It can program starting current equal to running current. The disadvantages of variable frequency drive is it is expensive, it is costly. The current drawn by these drives is non-linear, having harmonics, which causes a distorted voltage drop across the reactance of the generator. Since VFDs are non-linear, you must include an additional generator capacity sizing factor to keep the voltage distortion to a reasonable level of approximately 15% total harmonic distortion or less. The larger the generator, the greater the reduction impedance of the power source, which in turn reduces the effect caused by harmonic current distortion. So, Finally, we can see in this graph the different starting methods and the reduction in the starting current in each type of starters. As you can see, for the real starter, it's like approximately 6 to 8 times the starting current. Whereas when if you use a star delta starter, it's one third of the starting current, just times only of the nominal current, and a soft starter it will be 2 times of the nominal current. Whereas for VFD, it's almost very efficient way. It is almost equal to the nominal current. Yeah, thank you all for being there for today's webinar. I hope it was clear enough to you all.